experiments. So that's it. Only 3 are there today. What about others? Exam, huh?
Yes, sir.
No. Anyways, so we'll get started. There is one last chapter that is pending, that is the kinetic theory of gases, which I would like to explain today. Okay. So what I would suggest is just listen to the important points that I'm concentrating upon. Okay. And for this chapter, you can go according to the exam pattern. That's it. Just study for the sake of exam. And ensure you're concentrating more on oscillations and waves. Shall we get started?
Yes, sir.
One minute. Yeah, okay, sorry. Got a call. So, the kinetic theory of gases, right? There are certain important points that you need to concentrate upon. First is, they'll ask you about the postulates of kinetic theory of gases. So, what are the postulates? Means what are all the assumptions that we are going to take in this case? What are all the theory that was proposed for this chapter to be analyzed? Okay. First is, a gas consists of very large number of molecules. As the name of the chapter suggests, kinetic theory of gases. We know that gases consist of molecules which are loosely bound. Since they are loosely bound, they are going to have kinetic energy, and we are going to be concerned about the kinetic theory that is involved behind these gases. Okay, so basically, when you say a gas, it is taken that it consists of very large number of molecules, and the most important point is each one is assumed to be perfectly identical elastic sphere. First. Second, the molecules of a gas are in the state of continuous and random motion. We know that the molecules of gas are going to be restless and they will be in continuous motion. So they move in all directions with all possible velocities. They move in all directions with all possible velocities. Right. Next is the size of each molecule is assumed to be very small as compared to the distance of separation between them. So if you take two molecules, the distance of separation between them is going to be very much great compared to the size of the particle, right? Hence, what you can say is the volume occupied by the molecule is negligible in comparison to the total volume that is occupied by the gas itself. That is, if you take a container, in that container you will have many molecules that are present, and for those molecules, if you try to calculate the volume of each molecule, then the volume of molecule is going to be very less compared to the total volume of the gas itself. Next is, there is no force of attraction or repulsion that is going to exist between the molecules and the walls of the container. So if you take the molecules and the walls of the container, there is going to be no force of attraction or repulsion that is going to exist. And next is, the collision of molecules among themselves and with the walls of the container is assumed to be perfectly elastic. Therefore, what we can say is the momentum and kinetic energy of the molecules are conserved. So we know the fact that when you talk about the perfectly elastic collisions, the momentum and the kinetic energy of the particle is said to be conserved. Right. Next is, a molecule is assumed to move along a straight line between two successive collisions, and the average distance between the two successive collisions is what is called as the mean free path of the molecules. Means, if I take a container, if the molecule is getting collided with this wall, then it will go and hit the other wall and come back and hit this wall, right? So that distance, what the particle has traveled between two successive collisions is what we call it as the mean free path. And the seventh one is the collisions are almost instantaneous. That is, the time of collision that is existing between two molecules is negligible compared to the interval that is existing between two successive collisions. Okay. So these are all the postulates of kinetic theory of gases that you need to know. Based on these postulates only, we are going to do all the derivations that are there in this chapter. Okay. Is there any doubt?
Sir, can you repeat mean free path alone?
Okay. So the distance between two successive collisions, right? So if you take a container consists of, let's say it consists of two walls, and the particle is coming and hitting the container for the first time, then what will happen, since it's a perfectly elastic collision, the particle will revert back with the same velocity. Then it will go and hit the other wall of the container, right? So I'll call this as first collision. Again, it will come back to its original position. When it is coming, that is called as the successive collision. So that part is what is called as the mean free path of that particular molecule. So now try to understand. A molecule moves along a straight line between two successive collisions. So what do you mean by collision? Collision is the contact that is existing between the wall and the molecule. And the average distance between the two successive collisions is what we call it as the mean free path of the molecule.
Okay, sir.
Okay. Next is, you know what is an Avogadro number? Avogadro number is defined as the number of molecules that are present in 1 mole of a substance. It is constant for all the substance, and it is going to be 6.023 into 10 power 23 atoms or molecules, right? The next important point is they will ask you about the pressure exerted by a gas. So it is taken as the pressure exerted by the gas. So as we discussed from the postulates, we are clear that the molecules of a gas are in a state of random motion. So what will happen when they are in random motion? They collide against each other and the walls of the container. During each collision, what will happen is momentum will get transferred to the wall. So we know the fact that when the molecules are going and hitting the wall, then there is a force that is getting exerted by the molecule on the wall. And we know the fact that force is equal to dP divided by dt. Means when force is exerted, the momentum is changed. That is, it is transferred to the walls of the container. Then the pressure exerted by the gas is due to what? Due to the continuous collision of the molecules against the walls of the container. So what we are going to calculate is pressure. We know that pressure is equal to force divided by area, but force is defined as dP divided by dt and area is area only. Okay. So what we are trying to say is the pressure that is being exerted by the particles on the walls of the container is because of the change in momentum that is taking place due to this continuous collision. So due to this continuous collision, so read this, the pressure exerted by the gas is due to the continuous collision of the molecules against the walls of the container. So due to this continuous collision, what will happen is the walls experience a continuous force which is equal to the total momentum imparted to the walls per second. So amount of momentum per second is what we call it as force, and the force per unit area is what we call it as pressure. So the force experienced per unit area of the walls of the container determines the pressure exerted by the gas. Suppose, so till here it is the introduction to why pressure is existing within the gas particles. So did you understand it is existing purely because of the collision that is happening? So during collision, what will happen? Momentum is transferred, and when momentum is transferred, force is applied. When force is applied, pressure is exerted. Okay. Now we are going to start the derivation. So let us consider a cubic container of side L, and it contains n molecules of perfect gas. Perfect gas means ideal gas, moving with velocity c1, c2, c3, so on till cn. Okay, what did we consider? We considered gas molecules of side L containing L molecules of perfect gas. So, if you see, what we have done is we have considered one of the molecules and the molecule speed is taken to be C1. Then it is resolved into three components: U1 along x-axis, V1 along y-axis, and W1 along z-axis. So, figure beside shows a molecule moving with the velocity C1, having velocities U1, V1, and W1 as components of x, y, and z-axis respectively. Similarly, if you take U2, V2, and W2 are the velocity components of the second molecule and so on, then what we can do is we can consider a molecule P having velocity C1 colliding against the wall BCFG. So there is a wall here. Where is it? BCFG is a wall against which the particle is going and colliding. Now our job is to find what is the pressure exerted by that particle on that particular wall. Okay. So only the x component of the velocity of the molecule is relevant for the wall. This thing, because this direction the particle comes and hits. So it is only the x component that is going to contribute to the pressure that is being exerted on the wall. Right. Hence, the momentum of the molecule before collision is what? M into U1. And the momentum of the molecule after collision is also M into U1, but with a negative sign. So, what is the total change in momentum that is taking place? Delta P is equal to minus 2M U1. Are you guys able to understand what I'm trying to say?
Yes, sir.
So, when it is minus 2M U1, during each successive collision on the phase I, the molecule must travel a distance of 2L from phase 1 to phase 2 and back to phase 1. That is, this is phase 1, this is phase 2, between two successive collisions on the same wall. So when the particle is traveling from here and it is going hitting and again coming back to this part, how much is the total distance covered by the particle? Tell me. Let's say it has hit this wall and bounced back. Then it has to travel to wall 2. How much distance is it covering? L. Again, from wall 2, it has to travel towards wall 1. It is covering another L distance. So what is the total distance covered? The total distance covered will be 2L. And what is going to be the time that it takes between these two successive collisions? Time is equal to distance divided by speed. What is the speed of the particle along x direction? That is U1. Did you understand this fact? So delta P is equal to minus 2mu1 and T is equal to 2lu1. Then what is going to be the rate of change of momentum? Delta P by delta T is going to be how much? Minus 2mu1 divided by 2L divided by U1. So 2 and 2 will get cancelled. It will be minus M U1 square the whole divided by L. So minus M1. Okay, since we took it for the first particle, we'll take it as M1. Minus M1 into U1 square divided by L. And we know the fact that the rate of change of linear momentum is nothing but the force. So the force exerted by the particles on the wall itself is minus M1 U1 square divided by L. Is that clear till this step?
Yes, sir.
Right. So this is the force exerted by the wall on the molecule. Then what will be the force exerted by the molecule on the wall? It will be negative of this value. That will be M1 U1 square divided by L. Now, what is going to be the force exerted by all the N molecules put together? So what is the force that is exerted by all the N molecules put together along x direction? So F along x direction is M1 U1 square divided by L plus M2 U2 square divided by L plus so on till M1 UN square divided by L. Then what is going to be the pressure exerted by the molecules on the wall? Sorry, pressure exerted by the molecules on the wall in the x direction. So Px will be equal to Fx divided by A. Right? Pressure is equal to force by area. You already have the force and divided with area. We know that the area of each side of a cube is L square. So when you do that, you will get M divided by L cube into U1 square plus U2 square plus so on till UN square. Okay. Now you guys tell me what will be the pressure exerted by the molecule along Y and Z direction. It will be the same M divided by L cube. Now, did you understand why I replaced M1, M2 with M? Because all the molecules are taken to be identical. I told you in the postulates itself. So, M is taken out. M divided by L cube into V1 square plus V2 square plus so on till Vn square. Similarly, M divided by L cube into W1 square plus W2 square so on till Wn square. And since the gas exerts the same pressure on all the walls of the container, you know this fact, then Px will be equal to Py will be equal to Pz, provided here you ignore the effect of gravity. We don't take the effect of gravity, then we can say this, the pressure exerted will be the same on all the walls of the container. So what will be the total pressure exerted? Total pressure exerted will be the average of these three things. Right, when it is going to be the average, then pressure will be equal to M divided by L cube into U1 square plus U2 square plus so on till U1 square plus V1 square plus V2 square plus so on till Vn square plus W1 square plus W2 square plus so on till Wn square, right? And you will write 1 by 3 here. Is it clear till this step, guys? Any doubts?
Sir, U, V, and W are velocities along X, Y, Z axis, right?
X, Y, and Z direction. So that is those are the components of the velocity C along X, Y, and Z direction. Okay. Now, P will be equal to 1 by 3 into M by L cube into U1 square plus V1 square plus W1 square plus U2 square plus V2 square plus W2 square plus so on till UN square plus Vn square plus Wn square. This is what is happening. Then what you can say is C will be equal to root of U1 square plus V1 square plus W1 square. Then C1 is this thing. Then C1 square will be U1 square plus V1 square plus W1 square. Did you understand why I wrote it like this? C1 is equal to root of U1 square plus V1 square plus W1 square. Because C1 vector is equal to U1 I cap plus V1 j cap plus W1 k cap. Accepted? So what will be the magnitude of C1? Root of U1 square plus V1 square plus W1 square. We know that the magnitude of C1 is same as C1 itself. So what I can do here is pressure will be equal to 1 by 3 into M divided by L cube into C1 square plus C2 square plus so on till Cn square. Is that clear, guys? Is it clear till this step? So till this step, it is easy. What is the, if you see the whole process of derivation, right? What did we do? We found the momentum. We found the change in momentum, which was 2m1 minus 2m1 u1, or I can write it as 2m1 u1. We found the time between two successive collision, that is 2l divided by u1. Then we found the force, which is 2m1 u1 divided by 2l divided by u1. 2 and 2 got cancelled. Then you got m1 u1 square divided by l. Then you found the pressure along x direction. That was Fx divided by A. So m1 u1 square divided by L into A is 1 by L square. So you got m1 u1 square divided by L cube. Correct? And the total pressure is equal to Px plus Py plus Pz. So that is 1 by 3 into m divided by L cube into u1 square plus u2 square plus so on till un square plus v1 square plus v2 square plus so on till vn square plus z1 square plus z2 square plus so on till zn square. Right, then what did we do? u1 square, v1 square, z1, sorry, w1 square we combine. Guys, this is the shortcut to remember. Like, these are the steps, okay? I hope you're able to understand. I'm writing the same thing again. So u1 square, v1 square and w1 square you are going to combine. 1 by 3 into m divided by L cube into u1 square plus v1 square plus w1 square plus u2 square plus v2 square plus w2 square plus so on till this thing, last thing. So what will this give you? 1 by 3 into m divided by L cube into c1 square plus c2 square plus so on till cn square. This is the step at which we are standing. Any doubt? Any doubt?
Yes.
Clear, right? So this derivation, there is a possibility of you getting it. Now what we are supposed to do is, if I multiply with the number of molecules and divide it with the number of molecules, okay? Now tell me one thing, guys. C1 square plus C2 square plus so on till Cn square divided by the total number of molecules. What is it going to give you? If I give you 10 values, you add those 10 values and divide it with 10. What are you going to get? Okay, I asked you a simple question. Think about it. I'll give you 10 values, 10 numbers. I'll say add those 10 numbers and divide it with 10. What does that output mean? Is it not the average or mean? Similarly, can I call this as mean of square? Can I call this as mean of square right here? Right. So this will be equal to P is equal to M into N will give you the total mass of the gas. Correct? So M into N will give you the, see, M is the mass of each particle, N is the number of particles. Mass of each particle into number of particles put together will give you the total mass of the gas itself divided by L cube is volume, then this will be 1 by 3. Correct? Then can I write this thing as square root of C1 square plus so on till Cn square, the whole divided by N, the whole square? Did you understand what I wrote? So 1 by 3 into m divided by v into root of C1 square plus C2 square plus so on till Cn square, the whole divided by the whole square. So pressure will be equal to 1 by 3 into mass by volume is what? What is mass by volume? It is density. Then what is this thing, guys? I told you C1 square plus C2 square till Cn square divided by n is mean of square. Upper square root pota, it will become root mean square. This is a very, very important term. Mean square, sorry, root mean square, or it is also called as Rms velocity, which is defined as the square root of, see, name itself is suggesting root is square root, not cube root or fourth root. So square root of the average of all the square values. Okay, so that if I call it as C, then this will be C square. The pressure exerted by the gas on the walls of the container is given as 1 by 3 times rho into C square, where rho is the density of the gas and C is the root mean square value of the gas. As I mentioned, this derivation is very, very, very important and ensure you study it. Is it clear, guys? Yes or no?
Yes, sir.
Right. So the next question is the relation between the pressure exerted by the gas and the mean kinetic energy of translation per unit volume of the gas. So what are they asking? We need to find the relation between the pressure exerted by the gas and mean kinetic energy of translation per unit volume of the gas. So pressure exerted by the unit volume of the gas we have already found half 1 by 3 mn c square or 1 by 3 into rho into c square. Actually, there is a volume mistake. Okay, or it is 1 by 3 into rho into c square. Then mean kinetic energy, listen, mean kinetic energy of translation per unit volume of gas is how much? So mean kinetic energy means E is equal to, so if I take kinetic energy as half mv square, okay, I'll take it as half mc square and I will take this as capital M. Because I'm talking about the gas, mean kinetic energy of translation per unit volume of gas, per unit volume. So capital M divided by V is how much? Rho. It is half rho c square. Accepted, guys? So if I divide both, what will I get? Pressure divided by the kinetic energy. 1 by 3 rho c square divided by half rho c square, cancel these two, 2 by 3. So pressure is equal to 2 by 3 times the kinetic energy exerted by the molecules. Is that clear? So that is the relation between the pressure exerted by the gas and mean is average kinetic energy of translation per unit volume. Don't forget this, per unit volume of the gas. Is it clear?
Yes, sir.
So next we are supposed to calculate the average kinetic energy per molecule of the gas. So we are going to find the average kinetic energy of the molecule, average kinetic energy per molecule of the gas in terms of temperature. For that, what we will do is let us consider 1 mole of a gas of mass capital M and volume V. So there is a container in which there is 1 mole of gas, that is Avogadro number of molecules are present, and the mass of the gas is capital M and the volume occupied by it is capital V. So we know that pressure is equal to 1 by 3 times rho into c square. Pressure is equal to 1 by 3 into rho c square, and pressure is equal to 1 by 3 into capital M divided by V into c square. Can I write it? Because density is equal to mass by volume. So if I take the V to the other side, then I'll get P into V is equal to 1 by 3 into capital M c square. But what is PV for an ideal gas? We know that PV is equal to R into T. This will be equal to half into capital M into c square. Right? Now what I will do is, I will take the 3 to the other side. So 3 into R is equal to M into C square. Right? So what is M into C square, guys? Capital M into C square is what? Is it not the average kinetic energy per volume? Sorry, is it not twice the average kinetic energy per volume? So for that, what I will do, I will divide it on both the sides. I know this is the energy per unit volume that is going to exist. So this I will write it as half into. Now, if 1 mole of gas contains n number of atoms, where n is the Avogadro number, then how can I write the total mass of that particular gas? Can I write it as mass of each particle into capital Na? What is Na? Na is the Avogadro number, right? Now listen, I'll bring this R to the other side. Sorry, I'll bring Na to this side, not R. I'll bring Na to this side, and C square is there. Then I can write half into M into C square is equal to 3 by 2 into R divided by Na into T. Is there any doubt in this step? Is there any doubt in this step? I hope it is clear, right? Then this will be half mc square is equal to 3 by 2 into what is r divided by Na, guys? This r divided by Na is written as k into t, where this k is called as Boltzmann constant. And tell me what is this half into small m into c square, where small m is the mass of each particle.
Kinetic energy of this.
Sorry, it is a kinetic energy. It is a correct energy. What is it? Complete the statement. Kinetic energy
Of between particle of gas.
of each particle. So this is where the confusion starts. In the previous derivation, we wrote it as half rho c square. Another. What is half rho c square? It is the kinetic energy per unit volume of the gas. Okay, it is the kinetic energy per unit volume of the total gas. Whereas in this case, what is happening? Half into, you're writing it as m into c square, right? That is the kinetic energy of each particle. That is what they told, no? Average kinetic energy per molecule. So what is average kinetic energy per molecule? This is an important expression. It is 3 by 2 times K into T, or some books write it as KB into T, where KB is what is called as Boltzmann constant, and its value is 1.38 into 10 power minus 23 joule per Kelvin. So going forward, this is the value we are going to use. Average kinetic energy per molecule of the gas is equal to 3 by 2 times Kb into T. Okay. So from this point, there is a very, very important thing that we can derive is, if you take a gas particle, as you keep increasing the temperature, what is going to happen to the kinetic energy of the particle? It will also increase. That is what this expression says. Since it is clear that the temperature of gas is the measure of the mean translational kinetic energy per molecule of the gas. So they told it is not equal to, they didn't say that the temperature of gas is equal to the mean translational kinetic energy. It is a measure, means it is one of the parameters that is used to measure the mean translational kinetic energy per molecule of the gas. Is it clear? Guys, is it clear?
Sir.
Okay. The next one is degrees of freedom. So the name suggests degrees of freedom. I tell you one thing, is this chapter taught in your school? Did they complete it in your school? Okay, then everybody should be knowing these terms, right? Okay, so degrees of freedom means the name itself is suggesting. If you take a dynamical system, what do you mean by dynamical system? System where the particles are in continuous motion. Then if you take the number of degrees of freedom of a dynamical system, then there are certain, then it is defined as the total number of coordinates or independent variables required to describe the position and configuration of the system. So what they are trying to say is, when you talk about a gas molecule, so when you talk about a molecule, then that particular substance, a molecule, can have only translatory motion possible, or it can have a rotational motion possible, or it can also have a vibrational motion possible. So when you take a gas molecule, what are the three kinds of motion which it can exhibit? One is translatory, one is rotational, and the third one is vibration. Okay. So if I take a particle, which is moving in a straight line along any one of the axes, then it is said to have 1 degree of freedom. Means if the particle is confined to the motion along one dimension, it is said to have It is said to have 1 degree of freedom. For example, if you talk about an oscillating pendulum, it is said to oscillate along a particular path, which is having only a vibratory motion. It doesn't have any translatory motion. Secondly, a particle moving in X and Y planes simultaneously, okay, there's also an example only. A particle moving in a plane is said to have 2 degrees of freedom. What are they? An ant that moves on a floor. Right. Similarly, if you talk about a particle which is moving in space, it is said to have 3 degrees of freedom. Okay. You talk about a bird that flies. That is an example of an object which has 3 degrees of freedom. Now let me read this point. With this, you will understand. So if you take a point mass means just a point. A point mass cannot undergo rotation, but it undergoes only translational motion. Whereas when you talk about a rigid body with finite mass, it can have both rotatory and translatory motion. Okay. The rotatory motion can also have 3 coordinates in space like translatory motion. Therefore, a rigid body, if you take, will have 6 degrees of freedom, 3 due to translatory motion and 3 due to rotatory motion. So degree of freedom means basically in how many axes that particular particle is able to move will define the degree of freedom of that particle. So based on degree of freedom, we will be calculating an important parameter that is associated with the gas molecule, which is gamma. If you remember what is gamma, gamma is defined as Cp divided by Cv. That is a specific heat at constant pressure to the specific heat at constant volume. We'll be measuring it. Okay. So based on all these things, if I take a monoatomic molecule, since a monoatomic molecule consists of a single atom of a point mass, then it will have 3 degrees of freedom. Why? Because that particle can have a motion along, can have a translatory motion along X direction, can have a translatory motion along Y direction, and can have a translatory motion along Z direction individually. So it can either of the three things happen. Means it has the freedom to move in either of the axes. Performing a translatory motion, a monoatomic molecule is said to have 3 degrees of freedom. There is an important thing. It has 3 degrees of freedom of what kind? Of translatory motion. Similarly, when you talk about a diatomic molecule, what will happen? It will have two atoms are connected together to form a molecule. So diatomic molecule can rotate about any axis at right angles to its own axis. So this is the axis of that particular molecule, and this is the axis perpendicular to the axis of that particular molecule. So since it can rotate about a perpendicular axis to its own axis in 2 ways, then it has 2 degrees of freedom due to the rotational motion, and this particle as a whole can have translatory motion in 3 directions. So it has 3 degrees of freedom due to translational. So 3 due to translational and 2 due to rotational. So 3 plus 2 put together, it has 5 degrees of freedom, and the molecules which can have 5 degrees of freedom are O2, N2, CO, Cl2, all these things. Okay, that is what a diatomic molecule is. Whereas when you talk about a triatomic molecule, so when you talk about a triatomic molecule, in case of a triatomic molecule, you can talk about a linear type and non-linear type. So when you talk about linear type, the center of mass lies at the central atom. See, for example, if you take carbon dioxide will be something like this. Then the central molecule is said to be at the center of mass, right? So it behaves like a diatomic molecule with 3 degrees of freedom due to translation and 2 degrees of freedom due to rotational. So totally it has 5 degrees of freedom. Which one? A triatomic molecule, which is of linear type. Whereas when you talk about a triatomic molecule of non-linear type, then what will happen is it may rotate about any of the 3 mutually perpendicular axes. So therefore, due to rotation, it will have 3 degrees of freedom, and it will have 3 more degrees of freedom due to translatory motion along the coordinate axis. So this kind of a non-linear molecule will have 6 degrees of freedom that are possible. Okay, are you able to understand? So what is it? If you take a monatomic molecule has 3 degrees of freedom. Diatomic molecule has
5 degrees.
so 5 degrees of freedom. Triatomic molecule linear type is similar to a diatomic molecule, so it has 5 degrees of freedom, and the triatomic molecule of non-linear type has 6 degrees of freedom. Okay, having said all these things, we are going to see the last 2 important topics of this chapter, that is the law of equipartition of energy, and we will calculate the specific heat ratio, that is the value of gamma for a monatomic, diatomic, and triatomic molecules. Okay, so we get started. Listen to this carefully. So this is a very important one. What is the law of equipartition of energy? So law of equipartition of energy states that if you have a dynamical system in thermal equilibrium, then all the degrees of freedom are equally share the total energy of the system. So what they are trying to say is the total energy of the system is capital E. Then if you're talking about a particular gas where there is a monatomic molecule present. So monatomic molecule has how many degrees of freedom? It has
3
3,
degrees.
right? Then this energy will get divided into 3 parts along all the directions. That is what they're trying to see. In thermal equilibrium, all the degrees of freedom share the total energy of the system, equally share the total energy of the system. Okay. So we know that the energy associated per molecule is how much? 3/2 into kb into T. Correct? This we know. Energy associated per molecule, I already discussed, is 3/2 into kb into T. Then energy associated with each degree of freedom per molecule will be 1/3 of this value. That will be half into kb into T, where kb is called as the Boltzmann constant. Okay, for which they have shown a proof. It's a very simple proof. Anyways, I'll explain it. If you consider 1 mole of a monatomic gas in thermal equilibrium at a temperature T, then each molecule has 3 degrees of freedom due to translatory motion. According to the kinetic theory of gases, the mean kinetic energy of molecule is 3/2 times kb into T. So if you take Cx, Cy, and Cz to be the components of Rms velocity of the molecule along the 3 axes, then the average energy of gas molecule is given by 1/2 into mnc square is equal to 1/2 into m into cx square plus cy square plus cz square. Okay, so the sum of all these kinetic energies which are acting along individual direction put together is what is 3/2 into kb into T. Right? Since the molecules move at random, then what we can say is the average kinetic energy corresponding to each degree of freedom is the same. Means half mcx square is the same as half mcy square is equal to half mcz square. Then what I can write is 3 times half into m into cx square will be equal to 3/2 into kb into T. So 3 and 3 will get cancelled. Half mcx square, that is the kinetic energy associated with each degree of freedom, will be equal to 1/2 into kb into T. Don't be in a hurry to cancel half of, because this is the average kinetic energy per molecule per degree of freedom. Is that clear, guys? Is it clear? Any doubts?
No, sir.
Okay. The last part that we guys are going to see is derive the expression for the specific heat capacities, the ratio of specific heat capacity of monatomic, diatomic, and triatomic molecules. So applying the concept of law of equipartition of energy in specific heats of gas, we know one thing. We know that the Mayer's equation is Cp minus Cv is equal to R. And there is a parameter called as gamma is equal to Cp by Cv, where that gamma is what is called as the adiabatic component. And we saw why that gamma came also. I showed you the derivation. Right. So when you talk about a monatomic molecule, then the average kinetic energy, the steps that I'm going to tell you is the same for everything. So follow the same steps. Average kinetic energy of molecule will be how much? 3 by 2 times Kb into T. Then the total energy of a molecule of gas will be how much? So when I say average kinetic energy per molecule is equal to 3 by 2 into Kb into T, then the total energy will be equal to 3 by 2 into Kb into T. This molecule will go to the other side. We know that we have considered 1 mole of a gas. That is how this expression is derived. So it will be into Na. But what is Kb into Na, guys? Kb
R.
into Na is R. So 3 by 2 into R into T will give us the total energy of a molecule and gas. Then for 1 mole of gas, we know that the molar specific heat at constant volume, Cv, is equal to du divided by dt. And we know the internal energy it is possessed due to the kinetic energy of the molecules. So this will be 3 by 2 into R into derivative of T with respect to T is 1. So Cv is 3 by 2 times R. And we know that Cp is equal to Cv plus R. That will be 3 by 2 times R plus R. How much is this? 5 by 2 times R. Then what will be the value of gamma, guys? Cp by Cv is equal to 5 divided by 3. So for a monatomic gas, if somebody asks you what is the value of the ratio of specific heats, you will say it is 5 divided by 3, which is 1.67. Is there any doubt? Okay, next. For a diatomic molecule, if you see, if I calculate the average kinetic energy of a molecule, so according to law of equipartition of energy, each degree of freedom has an energy of half into Kb into T. For a diatomic molecule, how many degrees of freedom are there? They have 5. So this 5 will get multiplied with half into Kb into T. That will give you the average kinetic energy of molecule, which is 5 by 2 into Kb into T. Then what is the total energy of a gas molecule? That will be 5 by 2 into Kb into T multiplied with the Avogadro number. So Kb into Avogadro number is R. So it will become 5 by 2 into RT. And we know that Cv is equal to du divided by dt. So when you differentiate it, you will get 5 by 2 into R into derivative of T is 1. And Cp will be equal to 7 by 2R. Applying Cp minus Cv is equal to R. Then what is gamma? Cp by Cv, which is going to be 7 divided by 5, or that's it, 7 by 5. So 7 by 5 is also 1.40. Is it clear, guys? So for a diatomic molecule, when the value of gamma is 7 by 5, for a triatomic molecule of linear type, what will be the specific ratio of specific heats? What will be the ratio of specific heats in the case of triatomic molecule of linear type? So triatomic molecule of linear type, how many degrees of freedom? Same, huh? Will it not be the same?
Yes, sir.
Because that also has equal number of degrees of freedom. Okay. One last thing. So for linear molecule, oh, sorry. I think there is a mistake here. So when you talk about a linear molecule, it is again going to be wait, did I do a mistake? Correct only. See. Okay, leave this. Okay. When you talk about a non-linear molecule, then how many degrees of freedom does it have? 6. Then the total energy of molecules will be how much? Total energy of molecules will be 6 by 2 into Kb into T multiplied with Na. 6 by 2 is 3. So 3 times Kb into Na is R. So 3 times R into T will be the value. This is U. So Cv will be equal to du divided by dt. That is going to be 3R. Then what is Cp? Cp is equal to 3R plus R, which is going to be 4R. Then what is the value of gamma? Just 4R divided by 3R. Cancel it. You will get answer as 4 divided by 3. Okay. So that's it with this chapter. Okay. This notes, I will share it now itself. Just confirm if you have got it. Just a minute. Just a minute. So can you guys check your WhatsApp and tell me if you have received?
Yes, sir.
Got it, right? So this is the notes and you can just go through it for the last minute revision. As I told you, concentrate on the important points and go through the video again. That itself should help you. Okay. So that's it from my side. And you'll not have class tomorrow and day after. Okay. So I'll tell you when I can conduct a test from my side. I'll update on that. That's it from my side, guys. Anything else you want to ask me with respect to academics? Anything you want to ask me? That's it.
Yes, sir.
Okay, then we can wind up.